Matlab's y, where p is assumed to be 0, and you finally can find the result like this here. And you can easily check so all the conditions are satisfied. And also you can substitute the result back to the original differential equation. You will see that it is still satisfies the original differential equation. And this is the result. If you write it mathematically, the result should be something like this, where these four constants are the solutions to C1 to C4 with the initial conditions satisfied. And if you have even more complicated initial or given point, you can also solve the problem. However, the result could be quite complicated. You can still use it. So there are other examples you can solve it directly. I think this one is more difficult to solve than the previous one, because you can use the standard way to solve it. First, establish the solution, then describe the initial conditions, and then solve it. You can finally get the result. If you have two ordinary differential equations, you can also solve it. And you can use direct method to solve it. And to describe the two equations separately using quotation marks, the first equation and then the second equation. And then you can call the solve function to solve the result. And you can find x and y. Well, you can see that in y we have C1, C2, and C3. There are three undetermined constants. So in this way we can solve and we can find analytical solutions to certain differential equations. And also you can use Laplace transform to solve this kind of problem, but I'm not going to present it in this way. Because sometimes if you use this method, you may face problems. For instance, you have to consider the initial conditions, because you have to use Laplace transform to consider the initial conditions. So I would suggest we can use solve directly rather than indirect method. So just ignore this part. And for linear space equations, since the original analytical solution can be described in this way, we can easily use Matlab command. For instance, expm to calculate this part, the state transition matrix, and then use IMT to perform integration. So we can also solve the problem in that way. Up to now, that it seemed the function dsolve is quite powerful. It might be misleading to think that it can be used to solve any kind of differential equations. However, it is not the case. We know that for almost all the nonlinear differential equations, there are not any analytical solutions. So let's try to let me demonstrate to you through an example. Let's try this differential equation and find whether we can solve it using analytical method. For this equation, first we have to declare that it is not necessary actually to to use this command because t is not directly reflected here. So we can use the second command directly to solve the differential equation. If you define the first, if you use the first command, it is okay. So we can use this command to find the analytical solution to this differential equation. It is a non-linear differential equation. We have a square here and the multiplication of the right x terms. So it is a non-linear differential equation. However, with the use of DSOLVE, we can easily find the analytical solution of it. Now let's consider another differential equation. This is also non-linear. We just added a 1 to the right-hand side of this equation. Then I can use the same command. We have I maybe should omit this part because the independent variable here is still t. There is a mistake, I think. If you are trying to solve the differential, find the analytical solution, you will have a warning here. So there is no explicit solution to the original problem, unless the result is finally fine. But actually, no action has been taken to the original problem, which means that there is no analytical solution to the second example. It can be concluded that for almost all the nonlinear differential equations, there is no analytical solution. And for linear differential equations, we can find the analytical solution. And there are also examples, such as for the famous Van Ball equation, there is also non-analytical solution. So now the problem is, how can we study nonlinear differential equations? Because the analytical solutions may not exist, how can we study them? The only way is by numerical method. There is no other way. So we can only use numerical method to study nonlinear differential